Hello, and welcome. In this video, we will explore the principle of mathematical induction, a powerful proof technique essential for the IB mathematics analysis and approaches higher-level curriculum. By the end of this session, you will be able to use mathematical induction to prove statements about series and sequences. Mathematical induction is a method used to prove that a statement, often called a proposition, is true for all natural numbers or for all integers greater than or equal to some starting integer. Think of it like a chain of dominoes. To prove that all dominoes will fall, you only need to show two things. First, you must show that the first domino falls. This is our base case. Second, you must show that if any domino falls, the next one in a line will also fall. This is our inductive step. If both of these conditions are met, then you can conclude that all dominoes will fall. This is the fundamental logic behind mathematical induction. Let's formalize this. A proof by induction consists of three main steps. First, the base case. We must prove that the proposition, which we'll call P of n, is true for the first value of n, usually n equals 1. Second, the inductive hypothesis. We assume that the proposition is true for some arbitrary positive integer k. This is our assumption, our statement. Third, the inductive step. Using our assumption from the inductive hypothesis, we must prove that the proposition is also true for the next integer, k plus 1. This is our, then, statement. Finally, we write a conclusion. We state that because the base case is true and the inductive step holds, the proposition is true for all natural numbers n. This structure is crucial. Following it precisely ensures your proof is logically sound and will earn you full marks in an IB assessment. Let's begin with our first type of problem, proving formulas for series. You're already familiar with arithmetic and geometric series. Induction allows us to prove formulas for more complex series. A key concept here is the relationship between the sum of n terms, s sub n, and the sum of n plus 1 terms, s sub n plus 1. The sum of the first n plus 1 terms is simply the sum of the first n terms plus the n plus 1 dash th term. This identity is the bridge we will use in our inductive step. Let's work through our first example. We will prove that the sum of the series 1 times 3 plus 2 times 4, and so on, up to n times n plus 2, is equal to n times n plus 1 times 2, n plus 7, all divided by 6. This is our proposition, P of n. Let's follow our four-step process. Step 1. The base case. We must show that the proposition is true for n equals 1. For n equals 1, the left-hand side of our equation is just the first term of the series, which is 1 times 3, or 3. Now, let's evaluate the right-hand side for n equals 1. We substitute 1 into the formula. 1 times 1 plus 1 times 2 times 1 plus 7, all divided by 6. This simplifies to 1 times 2 times 9, which is 18, divided by 6, which is 3. Since the left-hand side equals the right-hand side, the statement is true for n equals 1. Our base case is established. Step 2. The inductive hypothesis. We assume the proposition is true for some arbitrary positive integer k. This means we assume that the sum of the series up to the k-th term is equal to k times k plus 1 times 2, k plus 7, all divided by 6. This is our key assumption that we will use in the next step. Step 3. The inductive step. We must now prove that if P of k is true, then P of k plus 1 is also true. Our goal is to show that the sum of the series up to the k plus 1 dash th term is equal to the formula with k plus 1 substituted for n. This is what we are working towards. We start with the left-hand side of the P of k plus 1 equation. We can split this sum into the sum of the first k terms plus the k plus 1 dash th term. Now, we use our inductive hypothesis. We replace the sum of the first k terms with the formula we assume to be true. This is the crucial step where we link P of k to P of k plus 1. Our task now is to simplify this expression and show it equals the right-hand side of our goal. Notice that k plus 1 is a common factor. Factoring it out gives us k times 2k plus 7 over 6 plus k plus 3. To combine the terms in the bracket, We find a common denominator of 6. This gives us 2k squared plus 7k plus 6k plus 18 all over 6. Combining the terms in the numerator, we get 2k squared plus 13k plus 18. Now, we need to factor the quadratic expression 2k squared plus 13k plus 18. We are working towards the form k plus 2, 2k plus 9, so we can anticipate these factors. Factoring the quadratic gives us k plus 2 times 2k plus 9. So our expression becomes k plus 1 times k plus 2 times 2k plus 9, all divided by 6. This is exactly the right-hand side of our goal. We have successfully shown that p of k plus 1 is true. Step 4. The conclusion. We have completed the proof. We write a formal conclusion. We state that the proposition is true for n equals 1, and we have proven that if it is true for n equals k, it is also true for n equals k plus 1. Therefore, by the principle of mathematical induction, the statement is true for all positive integers n. This complete structure is what is expected in an IB exam. Let's recap our learning objective for this section. We have successfully applied induction to prove a formula for a series. Now, let's move on to our second type of problem, proving formulas for sequences defined by recurrence relations. A recurrence relation defines a sequence by expressing each term in relation to the previous one or ones. For example, u sub n plus 1 equals 2 times u sub n plus 3. Often we can find a general formula, or closed form, for the nth term. Induction is the perfect tool to prove that this formula is correct. Let's look at our second example. A sequence is defined by u sub 1 equals 7, and the recurrence relation u sub n plus 1 equals 2 times u sub n plus 3. We want to prove that the general formula is u sub n equals 5 times 2 to the power of n minus 3. The process is very similar to series, but the inductive step will involve substituting the recurrence relation. Step 1. The base case. We check if the formula holds for n equals 1. The problem states that u sub 1 is 7. Using our proposed formula, u sub 1 equals 5 times 2 to the power of 1 minus 3, which is 10 minus 3, or 7. The formula works for n equals 1. Step 2. The inductive hypothesis. We assume the formula is true for n equals k. This means we assume that u sub k equals 5 times 2 to the power of k minus 3. This is our assumption for the inductive step. Step 3. The inductive step. We must prove that if the formula is true for n equals k, it is also true for n equals k plus 1. Our goal is to show that u sub k plus 1 equals 5 times 2 to the power of k plus 1 minus 3. We start with the recurrence relation for u sub k plus 1, which is 2 times u sub k plus 3. Now, we use our inductive hypothesis. We substitute our assumed formula for u sub k into the recurrence relation. This gives us 2 times the quantity 5 times 2 to the k minus 3 plus 3. Expanding the brackets, we get 10 times 2 to the k minus 6 plus 3. This simplifies to 10 times 2 to the k minus 3. We can rewrite 10 as 5 times 2. So we have 5 times 2 times 2 to the k minus 3. Using exponent rules, this becomes 5 times 2 to the k plus 1 minus 3. This is exactly the right-hand side of our goal. We have proven that the formula works for n equals k plus 1. Step 4. The conclusion. We write our formal conclusion, stating that the formula is true for all positive integers, n, by induction. Let's tackle a more complex case. Sometimes, a term in a sequence depends on two previous terms. For example, u sub n plus 2 equals 5 times u sub n plus 1 minus 6 times u sub n. This is a second-order linear recurrence relation. When the recurrence relation depends on two previous terms, our induction process needs a slight modification. We must prove two base cases for n equals 1 and n equals 2. Our inductive hypothesis must assume the formula is true for both n equals k and n equals k plus 1. Then, we prove it for n equals k plus 2. Let's work through our third example. A sequence is defined by u sub 1 equals 5, u sub 2 equals 13, and the recurrence relation u sub n plus 2 equals 5 times u sub n plus 1 minus 6 times u sub n. We need to prove that the general formula is u sub n equals 2 to the n plus 3 to the n. Step 1. The base cases. We must check for n equals 1 and n equals 2. For n equals 1, the formula gives 2 to the 1 plus 3 to the 1, which is 5. This matches the given u sub 1. For n equals 2, the formula gives 2 to the 2 plus 3 to the 2, which is 4 plus 9, or 13. This matches the given u sub 2. Both base cases are true. Step 2. The inductive hypothesis. We assume the formula is true for n equals k and n equals k plus 1. This means we assume u sub k equals 2 to the k plus 3 to the k, and u sub k plus 1 equals 2 to the k plus 1 plus 3 to the k plus 1. We will use both of these assumptions in the next step. Step 3. The inductive step. We must prove that if the formula is true for n equals k and n equals k plus 1, it is also true for n equals k plus 2. Our goal is to show that u sub k plus 2 equals 2 to the k plus 2 plus 3 to the k plus 2. We start with the recurrence relation for u sub k plus 2, which is 5 times u sub k plus 1, minus 6 times u sub k. Now, we substitute our two inductive hypotheses. We replace u sub k plus 1 and u sub k with their assumed formulas. Expanding the brackets gives us 5 times 2 to the k plus 1, plus 5 times 3 to the k plus 1, minus 6 times 2 to the k, minus 6 times 3 to the k. To simplify, we group the terms with powers of 2 and the terms with powers of 3. This gives us 5 times 2 to the k plus 1, minus 6 times 2 to the k, plus 5 times 3 to the k plus 1, minus 6 times 3 to the k. Let's simplify the first bracket. We can write 5 times 2 to the k plus 1 as 5 times 2 times 2 to the k, which is 10 times 2 to the k. So we have 10 times 2 to the k minus 6 times 2 to the k, which is 4 times 2 to the k. Similarly, for the second bracket, we have 5 times 3 to the k plus 1 minus 6 times 3 to the k, which simplifies to 9 times 3 to the k. So our expression becomes 4 times 2 to the k plus 9 times 3 to the k. We can write 4 as 2 squared and 9 as 3 squared. This gives us 2 squared times 2 to the k plus 3 squared times 3 to the k, which simplifies to 2 to the k plus 2 plus 3 to the k plus 2. This is exactly the right-hand side of our goal. We have proven that the formula works for n equals k plus 2. Step 4. The conclusion. We write our formal conclusion stating that the formula is true for all positive integers, n, by induction. We have now covered the core principles of mathematical induction for both series and sequences. Let's recap what we've learned. We've seen that a proof by induction requires a base case, an inductive hypothesis, and an inductive step. For series, the key is to split the sum s sub k plus 1 into s sub k plus the k plus 1 dash th term. For sequences, we substitute the inductive hypothesis into the recurrence relation. And for second-order recurrence relations, we need two base cases and two assumptions in our hypothesis. Now, to solidify your understanding and prepare for IB-style questions, here are 5 practice problems. Pause the video, work through them, and then resume to see the fully worked solutions. Here are the practice questions. They cover the types of problems we've discussed and are designed to challenge you at the HL level. Welcome back. Let's go through the solutions to the practice questions. Question 1 asks us to prove the formula for the sum of the first n squares. The base case for n equals 1 is 1 squared equals 1, and the formula gives 1. The inductive hypothesis assumes the formula is true for k. In the inductive step, we add the k plus 1 th term, k plus 1, squared, to the sum of the first k terms. We factor out k plus 1, find a common denominator, and simplify the quadratic to get the desired result for k plus 1. Question 2 involves a series of fractions. The base case for n equals 1 is 1 over 2, which is true. The inductive hypothesis assumes the formula for k. In the inductive step, we add the k plus 1 th term, 1 over k plus 1, k plus 2. We find a common denominator, which is k plus 1, k plus 2, and simplify the numerator to get k plus 1. This gives us k plus 1 over k plus 2, which is the formula for k plus 1. Question 3 is a first-order recurrence relation. The base case for n equals 1 is 3 to the 0 plus 2, which is 3. This does not match the given u sub 1 equals 2. This indicates a mistake in the problem statement, or the proposed formula. Let's assume the formula should be u sub n equals 3 to the n minus 1. In that case, the base case would be 3 to the 0 minus 1, which is 0, also not matching. Let's re-examine the problem. If u sub 1 equals 2, then u sub 2 equals 3 times 2 minus 4, which is 2. It seems this is a constant sequence where u sub n equals 2 for all n. The proposed formula u sub n equals 3 to the n minus 1 plus 2 is incorrect. This highlights the importance of checking the base case carefully. For the purpose of demonstrating the method, let's assume the problem intended for u sub 1 to be 3. If u sub 1 equals 3, the base case holds. The inductive hypothesis assumes u sub k equals 3 to the k minus 1 plus 2. In the inductive step, we substitute this into the recurrence relation, simplify, and show it equals 3 to the k plus 2, which is the formula for k plus 1. Question 4 is a second-order recurrence relation. We need two base cases. For n equals 1, the formula gives 1, which matches u sub 1. For n equals 2, the formula gives 5, which matches u sub 2. The inductive hypothesis assumes the formula for k and k plus 1. In the inductive step, we substitute both into the recurrence relation, expand, and group terms with powers of 4. This simplifies to 2 times 4 to the k, minus 1, which is the formula for k plus 2. Finally, question 5 involves factorials. The base case for n equals 1 is 1 times 1 factorial, which is 1. The formula gives 2 factorial minus 1, which is also 1. The inductive hypothesis assumes the formula for k. In the inductive step, we add the k plus 1 th term, k plus 1, times k plus 1 factorial. We factor out k plus 1 factorial, leaving k plus 1. This simplifies to k plus 2 times k plus 1 factorial, which is k plus 2 factorial. So we have k plus 2 factorial minus 1, which is the formula for k plus 1. That concludes our session on mathematical induction. We have covered the fundamental principles and applied them to prove statements about series and sequences, including those defined by first and second order recurrence relations. Remember, the key to success is to follow the structured four-step process: base case, inductive hypothesis, inductive step, and conclusion. Practice is essential to master the algebraic manipulation required in the inductive step. Thank you for watching. Keep practicing, and you'll become proficient in this powerful proof technique.